Hey everyone, Christian here from Hulteberg Chemistry Engineering to give you another webinar today on the very fascinating topic of oil refining. I work a lot with renewables, but oil refineries are truly fascinating. They're like kindergartens for chemical engineers. They contain everything from thermal, catalytic, and physical unit operations to make us happy. Hulteberg Chemistry and Engineering. We are a small specialized engineering firm working with heterogeneous catalysis. We work all the way from research through development and upscaling, and we can help you anywhere from idea to implementation. All right, so what will we be talking about today? Well, first of all, there will be an introduction. There will be some input on why we do oil refining and so on. There will also be background. We'll try to sort out some of the concepts like proven reserves and the different fractions that we produce. Then we will go through the bulk of the unit operations, breaking it down into physical, thermal, and catalytic processes. A few words on the future trends, and then finally some conclusions. So why do we do oil refining? Well, first of all, it's for the production of fuel. So oil by volume or mass is mainly going to the fuel pools, but it's also for the production of specialties, and we see also chemical intermediates coming out of this for petrochemicals. And if you break down the oil barrel, you can see that about 71% is the fuels, or 70% is fuels. We also get heavy fuel oil, and we get some petroleum coke. This is 6 and 5% here. We get some gas, we get some residual fuel oil, and then this 4% here is finished chemicals and feedstocks for chemicals. We get asphalt, we get liquefied petroleum gas or LPG, and then we get some lubricants, we get some specialty naphthas, we get waxes, and finally some other products. So there's quite a lot of things that we get out of the barrel or the drum, but the majority, the very bulk, goes into making fuels. The interesting thing is that the value of these products, so the 4 orange percent is actually on par with respect to how much money we make as the 71%. So chemicals are actually an important part of the financial viability of oil refining. So today we are in a situation where the world demands lighter and cleaner products. So we want things that burn better with less sulfur. And at the same time, we have consumed a lot of the good stuff. So the easy access, low sulfur oil has already been used. So we tend to go to heavier and more polluted crude oils from less conventional places to pick them up, like oil shale and things like that. The refining well capacity has increased over the years. So we can now roughly process about 100 million barrels per day. But the utilization factor is, as you can see here, the green bar actually is about 80%. So there is some overcapacity also when refineries are running at its high point. Chemical industry is also important, as I mentioned, because of the high value created by the chemical part, and there's a strong industrial symbiosis, and there is indeed quite a lot of crossbreeding and cross ownership between oil refining and bulk chemical plants. If we look at operating costs, the fixed cost and the cost of capital is actually the majority of the production. So if you want to refine 1 barrel of oil, you actually have to, 1 ton of crude, the variable cost, so the influence of the utilities and other things are much, much lower, about 10% compared to the fixed cost. There is about 650 refineries globally, and they range from being simple refineries that we call topping, which is basically just a simple distillation operation where we just separate products on boiling point. We have hydroskimming, where you also use hydrogen in the production. So you have certain unit operations that gives you hydrogen, the reforming, for instance, and that hydrogen is used, for instance, for purification or hydrotreating. And that's called a hydroskimming refinery. The cracking type refineries is sort of a medium treatment where we also do some upgrading of the heavies. So the heavy boiling point hydrocarbons is turned into lighter ones in a catalytic cracker. And finally, we have coking refineries where you do a lot of upgrading also to the heavies. And then finally, we have one category, which is specialty refineries, which are, of course, focusing on other things than fuels, mainly fuel oils or lubricant oils and waxes and things like that. So there are these 5 types of refining, ranging from simple to very complicated, and you also have specialty refineries. When we talk about the reserves, where we get the hydrocarbons from, the crude oil, you normally hear about reserves, you hear about the reserve base, and you hear about resources. And for something to be classified as a reserve, it has to be economic, it has to be demonstrated, then it's classified as a reserve. If there is believed to be more resources and they will make economic sense probably in the future or just break even today, that's what we call the reserve base. And if it's non-economic to extract the oil and it's undiscovered, we call it resources. Or actually, resources also include the reserve base and the reserve base include the reserves. So it's just the definitions. And that actually means that the reserves will vary. So over time, we get improvement in technology, so we can make extraction of hard-to-get oil more economically feasible. We also see a change in economy, that you have a variation in the price of oil. The higher, the more unconventional oil you can extract. And there is changes to the demands we put on environmental protection. So the more environmental protection restrictions, the less value high sulfur or vanadium feedstocks will have, for instance. So resource depletion is really dependent on all of the factors above. And economic depletion is where there is the same cost for extracting the oil and producing oil from them. So there is really no point in bringing oil out of the ground. And to answer the question that everybody poses in oil context, will the oil ever, will there always be oil? The answer is yes. The question is if it will be economically viable to extract it from the ground, but it will never end. We also use different measures to categorize the oils. So one of those is API gravity, which is a measure of how dense the oil is. Water has an index of 10 degrees API. We use the term light crude if it's between 30 and 40. We use medium crude for 20 to 30. We use heavy crude for 10 to 20 API. And if it actually sinks in water, it's extra heavy. We also talk about sulfur content, and we use the terms sweet and sour. And if it's below 0.7% sulfur, it's termed sweet crude. And if it's above 0.7, it's sour crude. These oil sands, oil shale, bituminous oil are all extra heavy, and they require quite severe pretreatment before they can be processed in traditional oil refineries. And if you look at these crudes, they are strongly dependent in quality from where they are extracted. So the reservoir, how they have been formed, also shapes their characteristics. So there's very large crude quality differences between different geographic regions, but there are also quite significant differences between wells at the same geography. To make this simpler, this is in fact the world's largest traded commodity, so we have to be able to discuss and talk about these qualities. And to do that, we define benchmark qualities. And if you plot different benchmark qualities with respect to sulfur content on the x-axis and the density on the y-axis, you can plot them here like this, and you see that the two most commonly discussed, WTI, West Texas Intermediate, and Brent, are found here. So they are very light and they're very low in sulfur. Other benchmarking qualities like Arabic Light or Maya can be much higher in sulfur, and they are also more dense. And then what we do is that we take the specific oil that we have extracted from our well and we compare it to, for instance, Brent, and we say that it's a little sweeter and it's a little lower in density. So then we get a premium compared to the Brent for having lower sulfur, but we may have a discount because it is more dense. So you compare your individual oil that you have produced to these qualities, and then it's priced accordingly. And if you look at what we produce, we see a multitude of outputs. So LPG, liquefied petroleum gas, is one of the fractions that we get out of the refinery. It's a fuel for first and foremost, but it's also a chemical intermediate. You can use it for cracking, for instance, to produce propylene, ethylene, gasoline, diesel and heating oils. We get kerosene, jet fuel range. We get heavy fuel oil, which is used for marine applications and also for heat and power. We get a naphtha fraction, which is used for cracking into ethylene propylene. So it's important to be low in olefin content, as well as being rather straight chain, no aromatics and naphthenes. We get products from the heavy end, like coke and asphalt, which find their use in different ways. And we get lubricants from the specialty refineries, and also oxygenates can be produced in refineries for making anti-knocking additives, etc. And if you take and you break down these products and plot them in a diagram like this and compare the boiling range, which you have here, to the approximate carbon number, you get something that looks like this. That LPG is of course the lightest one. It's condensed gas, so you have to have it at pressure at room temperature to keep it liquid. Naphtha and gasoline are quite low in boiling point, followed by the aviation gasoline and the jet fuel. So these two qualities are somewhere in the end of the automotive range. Kerosene and diesel fuel overlap to some extent. We also get the heavy fuel oil, but then we're above 300 degrees in boiling point. We get paraffins, we get lubricant oil also in this 25 to 50 carbon atom range, 300, 400 to 600 degrees boiling points. We have our waxes, and then at the very top we have asphalt and petroleum coke. And of course, here you can't really talk about a boiling point. We'll get back to that as well. We use some trivial names, and the trivial names can be difficult because, well, you have to know them to know what they mean. We talk about paraffins, which is alkane hydrocarbons. We talk about isoparaffins, which is branched alkane hydrocarbons. We talk about olefins. I actually already did that, but that's alkenes, so unsaturated hydrocarbons. We talk about alpha olefins, where the unsaturated bond is on the first carbon of or the last carbon, but yeah, the first carbon. We talk about naphthenes, which is cycloalkanes, and of course aromatics are aromatics. They contain a benzene ring. When we're talking about definitions, we also have definitions for the gasoline and the diesel and actually all other qualities that we get out of the refinery. But gasoline and diesel, since they're such major products and they're so important that they're right in quality, there's quite a lot of measures that it needs to be fulfilled. Two of those are actually how well they perform in the engine. And we talk about the octane number for gasoline, where you see how the knocking tendency in a spark ignition engine is, how sensitive is it to compression, how sensitive is it to self-ignite during compression. And you use a mixture of N-heptane, which represents 0, and isooctane, which represent 100. And then you compare the mixtures of these to your actual gasoline, and you end up somewhere in the 70 to 100 something range to be able to sell it. And we differentiate between motor octane number and research octane number, which are basically two ways of performing the same test. And in certain geographies, Sweden for instance, we use the motor octane number. In other regions, you use the research octane number. And just to make it simple, you in some regions use the arithmetic mean of the two. So you take the motor and the research octane numbers, you sum them together, and you divide by 2. So just because it says 95 octane, you need to check which method has been used to determine that, to know how it compares to what you're normally used to. Diesel, on the other hand, has its own measure, which is the cetane number, and it measures sort of the auto-ignition capability of the fuel. So when you compress the fuel, how prone is it to ignite? And we do the same thing. We use cetane, which is 0, and alpha methyl naphthalene, which is 100, and then you get a number, and it's usually somewhere between 45 and 70, so in that medium range for the diesel. Then there is quite a lot of seasonal variations, and that relates to vapor pressure, ignition temperature, viscosity, and things like that. So in cold parts of the world in the wintertime, you can't use the same vapor pressure for gasoline, for instance, because then there won't be enough vapor to ignite the engine. So you have to actually use a lower vapor pressure in the winter, and you can use a higher vapor pressure in the summertime. But in refineries, we not only produce fuels and products, we also form wastes. And there is quite a significant amount of wastewater in the form of cooling, so which is not really contaminated, but it's contaminated with heat. So you have to have a recipient ready to take the amount of water that is produced and dissipate the heat. So between 3.5 and 5 cubic meters of wastewater. We also get polluted wastewater, and in that polluted wastewater, we have about 100 to 300 milligram of oil. In the desalted water, we get about 5,000 milligram per liter of oil in tank bottoms. We get benzene, we get heavy metals in these polluted wastewater. So we need a really nice wastewater treatment plant. Aside from wastewater, we also get solid and sludge waste, which is about 3.5 kilograms per ton. And most of this is hazardous waste because of the heavy metal and the toxic organic substances inside. We also do get volatile organic carbon emissions, so hydrocarbon leakage, for instance, from tank breathing operations and other diffuse emissions, which will contribute to smog and other things. So about 0.5 to 6 kilograms of 1 ton of crude is lost in these type of emissions. And then, of course, there are other emissions like BTX, benzene toluene xylene. There are sulfur oxides and nitrogen oxides that needs to be taken care of. And SOx and NOx are more and more stringently treated nowadays. Okay, so I talked quite a lot about oil refineries, but this is the first time I actually show you a schematic of an oil refinery. As you can see, we have crude oil coming in to the left here. And the first thing that happens is that it goes into a fractionator. We send it into an atmospheric distillation unit where we separate the compounds in the oil with respect to boiling point. So we get the very light in the top, we get gasoline fractions, we get naphtha fractions, we get middle distillates, and we also get heavy components, heavy atmospheric gas oil, we get vacuum gas oil, and we get other very heavy vacuum gas oils down here. And they're sent to different types of upgrading. Some of the hydrocarbons can actually be used directly. We call it straight run, when they go directly from the distillation tower to the product pool. But this is quite uncommon. The most common thing is that we use catalytic unit operation, which is the blue squares here, to somehow change the hydrocarbon. So naphtha can be hydrotreated to get rid of nitrogen, sulfur, and oxygen compounds. And then we can do catalytic reforming, which changes the structure of the hydrocarbon from long straight chained into branched hydrocarbons. And then that is transferred into gasoline components, and at the same time we get some hydrogen that we can use in other places in the refinery. The same thing can be done with other parts of the feedstocks. So heavier stuff can be treated and cracked down into smaller parts, producing more gasoline, either with hydrogen or without hydrogen. And we also get things done with the very heavy parts, like getting rid of asphalt. And down here on the heavy side, we also see two red squares, which represent thermal unit operation. So coking and visp braking do things to the very heavy part of the hydrocarbon fractions. So let's start and talk about the physical refinery processes, which in this process flow diagram is represented with white squares here. So we have a few of them. And of course, the first thing that we need to do is to make sure that our crude oil is clean enough to actually go into the distillation unit. So we have to do something that is called crude desalting. And after that, we do crude distillation. And on the very heavy side, we do have to remove asphalt components. So we do something that is called propane deasphalting. And yeah, that's a solvent extraction, which is also existing in the refinery. And if you look at crude oils, you get crude, and inside the crude oil, there will be small water droplets that has emulsified, so a water in oil emulsion. These emulsions will contain different salts like sodium chloride, magnesium chloride, calcium chloride, and these salts will cause severe problems in your refinery because a refinery is not built out of stainless steel, so you will get quite a lot of corrosion if you have chlorides coming in. You also get catalyst poisoning, and you will also cover the heat transfer surfaces in furnaces and heat exchangers with these salts, and they will stop transferring heat. Therefore, oil has to be desalted, and we do this in 4 steps. First, we wash it with water, the incoming crude oil. We heat it, and then we have it sit in an electrostatic field. And using the electrostatic field and the charges of the ions, we separate them from the crude oil. And then there's a settling part. And you can, with this treatment, do about 90% removal in one single step, and therefore it's quite common that you do the same thing twice so that you get above 90%, maybe 99% purity before going into the refinery. And in the refinery, we have what we call the crude oil distillation unit, the CDU. This is the first refinery unit, and these are huge, very large units. So they can process between 1,000 and 50,000 tons per day. They also represent the highest operating cost in the refinery, where a lot of the hydrocarbon that is put in is converted to heat and used to drive the boiling reactions, or well, boiling, not the reactions, the boiling. It's used for initial fractionation of the crude, and the crude is initially fractionated to get the different boiling point range fractions out of the oil. And these boiling point fractions actually to some extent represent molecular size. And that's true for the hydrocarbons. But if you look at hydrocarbons that contain a heteroatom, like sulfur, oxygen, they will be overrepresented in the heavy part. In the CDU, the crude is preheated before it enters, and then the heating goes up to about 300 to 350 degrees. And if you look at the towers, it's not just a simple distillation operation. There is actually quite a lot of circulation of reflux. You have different side draw products, and you strip these with steam. If you look at the column, it's about 30 trays, and one tray is about a meter, so somewhere between 30 and 40 meters high. Interestingly, all these distillation operations are limited to about 350 degrees, and when we pass 350 degrees, we get a significant solid carbon formation. So we can actually not go above 350 degrees. Otherwise, we risk filling our distillation unit with solid carbon, and we don't want it there. And if you want to further separate things that boil above 350 degrees, we do that using vacuum distillation. So instead of increasing the temperature in the first column, we take the bottoms of the first column, which is exiting at the 350 degrees C, and we put it into a distillation column where we reduce the vacuum to below 100 millibar, and we continue the separation to get better upgrading of the total hydrocarbon content. The bottoms from the vacuum column is actually sent for either cracking and or coking. So that's where we get the really heavy stuff out. And there's about 10 fractions leaving the CDU with different boiling point intervals. And here we define the end point. So that's the highest boiling point of the actual hydrocarbon fraction. So off gas starts at quite significantly below zero, and it ends at about 10 degrees. Then we talk about light straight run naphtha from 10 to 70, naphtha 180 degrees, and so on. And you see that the vacuum gas oil boils at 390 degrees and vacuum distillate at 550, which means that has to be separated under vacuum, otherwise we will get solid carbon formation. If you look at the process flow diagram, we get our crude desalted oil coming in up here. We use a circulating reflux to preheat the incoming crude oil, but at the same time we're also cooling the oil at this point to create a better separation. We do this twice in different sections in this column. Then we do the final heating in a furnace, and this is where we consume a lot of the energy that is needed or to fuel the entire process. And we go into the bottom of the column. Here we also add a little amount of steam to help further the separation of different components. And then we do side draws, so we extract hydrocarbon fractions at some points. We do a flash, so we separate them. And again, we use steam to further the separation. This is then cooled and it's separated in a different column. And yeah, it goes back again. And we can do this in multiple places. And from this hydrocarbon fraction, we get light gas oil. From the second side draw, we get kerosene. And in the top, we condensate, we get a reflux return, again, to improve separation. We get water separated and we get gases. That is our LPG and other low BTU gas that can be used in the refinery or sold as products. And this light fraction here is naphtha. The very heavy bottoms goes from the main fractionator, and it's further heated under vacuum, and you go into the furnace here and you do vacuum distillation here, and you get a light gas coming out which is condensed, and then you get a combination of water and oil here. We get some side draws here with intercooling to get intermediate gas oil. We get the same thing here in the bottom, which is the heavy gas oil. And finally, in the bottom, we have the vacuum residue. And let's continue talking about these heavy parts, the heavy gas oil and the vacuum residue. And the first thing that we need to do, if we want to continue to upgrade these streams, is to get rid of asphaltenes. Asphaltenes are large hydrocarbon molecules which are to some degree at least aromatic in content, and they are mainly insoluble in most things. So they're basically pitch, and we want to get rid of these, otherwise they will form carbon in downstream processes and it will complicate these processes significantly. And what we do is actually separate these molecules from the rest of the oil by dissolving the rest of the oil in a paraffinic solvent, something like C3 to C7. And in this case, it's called propane deasphalting because we use propane. We do this at 100 to 150 degrees and at elevated pressure. And if you look at the process flow diagram, we take the vacuum residue, we go into a column where we allow this vacuum residue to contact liquid propane. In the bottom, we get everything that is not soluble in the propane. So here we get a solution, or actually that isn't dissolved. So the asphaltenes and some propane end up here in the bottom. They are cooled, and then we flash to get rid of the additional residual propane. And the asphaltenes are again stripped to get any hydrocarbons out of there that aren't asphaltenes. And then finally we end up with an asphalt stream. Up here, we take the rest of the stream, so this is a liquid column. We take the propane and we evaporate it. So we heat it up to vaporize the propane. We go into a flash vessel where we separate the propane and it's recycled. By condensation, we can use it again. And finally, we go again to a stripper to get rid of additional propane, and we end up with the same oil as we came in with, but without the asphaltenes. So to summarize, the crude distillation unit is really the heart of the refinery. It's done in two stages, atmospheric and vacuum distillation. Maximum temperature, 350 degrees, important to avoid carbon formation. We have about 10 fractions leaving the unit. And then if you look at the propane deasphalting, it's a pre-treatment. So you can call it a pre-treatment because we get rid of these very carbon forming components, and it makes it better for further upgrading in, for instance, fluidized catalytic crackers. The thermal refinery processes, if we turn to them, is all focusing on residual upgrading. We talk about visbreaking, which is mild thermal treatment that reduces the viscosity of the oil. We talk about delayed coking, which is a quite severe treatment, but not as severe as flexi coking. The purpose of these are to form lighter cracked products from the very heavy fractions, but we also, as a side product, get heavy residues as well as coke, and the coke can actually be upgraded and used for other things. And basically, you take your saturated compounds, you add heat, and they break down into saturated and unsaturated compounds as well as light gas. These unsaturated can form free radicals, and with more heat form lower boiling unsaturated and gas, but they can also close on themselves to form aromatics and other low unsaturated and gas. These aromatics can in turn, with more heat, form lower boiling aromatics as well as unsaturated and gas, and these aromatic free radicals can combine, and when they combine they will form solid carbon. And the same thing happens for very large molecules like resins and asphaltenes. They form with heat solid carbon as well as lower boiling aromatics, unsaturated and gas. And when you look at, for instance, vis breaking, there is several fractions formed. You get about 2 to 4% gases, you get naphtha 5 to 7%, you get gas oil, so boiling 165 to 350 degrees, 10 to 15%, and then you get the cracked residue. Not much carbon formation in this process, but still some. So what happens in the vis breaking, which is a mild treatment, is that you break the paraffinic side chains. You do some cracking of naphthene rings, so you open up ring structures, and you do get coke formation from polymerization, condensation, dehydrogenation, and dealkylation reactions. Process flow diagram is quite simple. You take your vacuum residue, you heat it up, you take it through a reactor, and in the reactor, just having heat, allowing the heat to act on the in the oil, you get these reactions we just discussed, and then you cool it down, or you flash it actually hot. You take the gas and you separate it with gasoline. You take the other residual liquid part and you get the heavy gas oil and the cracked residue. And if you look at operating conditions, this is done at about 440 to 480. So since we're above 350, we will get coke. But by limiting the time to about 1 to 8 minutes, we can control the carbon formation. And this is done at 3 to 20 bar just to keep the hydrocarbons in the liquid state. So depending on the boiling point of the vapor pressure, we might need different pressures. Next step in severity is what we call delayed coking. Here we have much longer residence time and we have higher temperature compared to vis breaking. And this is something as unusual as a batch process in a refinery. Otherwise we see mainly continuous processes, but here we have coke drums which are deposited, and then you stop operation, and then you go back and you clean them. You enter the heated oil into the coke drum. You can see here's a decoker with 4 drums, and the volatiles, so you enter the oil through the bottom, the volatiles goes out in the top, which is the hydrocarbon fractions and some gas formation. The solid carbon is deposited on the inside. You go in at about 500 degrees and you exit at about 440. And then, yeah, depending on what pressure you have, you get different qualities of the coke. What we produce is unsaturated gases like ethylene, propylene, butylene, etc., and as well as methane, significant amounts of methane, ethane, propane, and so on. The gas, the liquids are about 70% together, and the coke is about 30% or less. The gas that comes out here can be used for alkylation. We will talk about gasoline later. We will also see it used as LPG. The liquid is sent for gasoline, and coke is used for different things depending on the process. The different types of coke that you can produce is shot coke, and you do that if you have a low pressure process with high sulfur containing feedstock and also quite high metal content, and it's basically used as solid fuel. If you increase pressure, have a lower sulfur and metal content, you can actually produce sponge coke, which can, for instance, be used for making anodes in the aluminum industry. And finally, if you go to high pressure, have a high aromatic and no asphaltene feedstock, you can actually produce needle coke, which can be used for making more advanced graphite electrodes. And as I said, this is a batch process. So we start by filling the coke vessel with solid carbon. Then from the top, we actually insert a drill and make a hole in the carbon, and then we use the same rod for washing the carbon out with water, and it falls down here, and then the coke needs to be dried. And decoking takes about 22 hours, something like that, if you put a figure to it, and you normally operate one of these coking vessels for about 24 hours. So there's some lead time. But this is, as I said, batch-wise, so this has to be decoked once every day, so to speak. Looking at the process flow diagram, we take our vacuum residue, we put it into a fractionator, and if there are any light ends in the vacuum residue, we will actually get them out here first. So we only send the really heavy stuff to coking. We take it and then we increase the heat to the 500 degrees we talked about later. We put it into one of two coking sections, and they can be one or two or more vessels per section. The coke is deposited, so we in one vessel deposit the coke, and in the other we extract it in parallel by cooling it down, and etc. We then take the liquids that are formed, put them into the fractionator. We take the heavy stuff, still heavy, going back to the cracking, and then, coking. And then we add a side draw here in the middle, extract the gas oil. In the top, we get naphtha and we get gas. And decoking is about 22.5 hours, but these are of course rough numbers. So half an hour for switching, 6 hours for steam cooling, 7 hours for decoking and draining, and then you have 9 hours to heat it up again, and you have about 1.5 hours in contingency. Flexi-coking, which is the final one that we'll go through, is when we, instead of making too much solid carbon, produce a fuel gas instead. So this process minimizes actually coke formation and the net coke formation, and it instead produces a low BTU gas that can be used as a fuel in the process or in the refinery. So what we do is we take the same residual, we put it into a reactor where it's contacted with hot coke. So hot carbon is used for transferring the heat and heating the reactant up, and that's where we get the cracking reactions and we get some lighter products. So we form products that are fractionated, we go to liquid products, and we go to gaseous products. And we, as a result of this, also get some solid carbon formation, which is now cooled down. It's not cold, but it's cooled down. This solid coke is taken to a heater where it's again reheated and it's returned to the reactor, or part of it. The other part of the solid carbon is actually taken out and sent to a gasifier where we use air and steam to turn it into carbon monoxide, methane, CO2, hydrogen to form a low BTU gas. Part of that low BTU gas is used in the heater for fuel, but most of it is sent to removing of the fines, so it's coke in the gas stream, as well as getting rid of sulfur and all other things. And we end up with a sweet low BTU gas that can be used as a fuel gas in the refinery. We do have a net coke production of about 1 to 2%. So in this case, we're not producing solid carbon. Instead, the product is a sweet low BTU gas, which can be used for fueling the rest of the refinery. So to summarize, thermal treatment is really important for upgrading heavies. And we range from mild with visp breaking to very severe in treatment with the flexi-coking. And the solid carbon formed may actually be a product with some value. All right, final section will be catalytic processes. So we talk about catalytic cracking, we talk about catalytic reforming, alkylation, and then there's some hydroprocessing, both hydrotreating and hydrocracking. And if we start with hydrocracking, this is the largest example, the largest catalytic process in the world with respect to catalyst volume. And it's used to increase the gasoline production. And it takes heavy oil fractions, like vacuum gas oil, and we use a solid acid as a catalyst, normally a zeolite. And there's all sorts of reactions going on. We break carbon-carbon bonds, we do isomerizations, we do protonation, deprotonation, there's alkylation going on, as well as polymerization, cyclization, and condensation. And here we are, sorry about that. And what happens is that we take an intermediate, we form a carbocation. So we take hydrocarbons, we add a proton, we then form this carbocation using the acidic sites of the catalyst, and after dehydrogenation, we end up with a positive carbocation that continues the reaction. It's also the first large-scale application of fluidized beds, this unit operation. This carbocation can do all sorts of reactions. So we see initiation reactions forming the carbocation. We see cyclization going on where it's protonated. We also see branching and cracking reactions, and then we reform the original hydrocarbon, but in a smaller form. So forming unsaturated molecules and things like that. And if you take it one level higher, we actually see that branched aromatics crack down into aromatics as well as small alkanes. If we have long chain alkanes, they form branched alkanes and alkenes, as well as smaller alkanes and cycloalkanes. The cycloalkanes can be transformed into aromatics, and the smaller alkenes into branched and small alkenes. And this carbenium ion is more stable in the tertiary than the secondary than the primary form, and ethyl and methyl groups are less stable than those. And if we form alkenes or olefins, the alpha olefin or 1-alkene will form. Another feature with this reaction is that if you have less than C7, so 7 carbon molecules, they will most likely not react. And if we compare the thermal cracking to catalytic cracking, we see that we can significantly increase the yield to the C3 to C8 range, and C3 to C8 is where we want a majority of our product to go if we want to make, for instance, gasoline. Thermal, we end up mainly with ethylene. Process flow diagram, we take our feedstock, we put it into a reactor, we let it contact the catalyst, and the reaction happens in this riser tube here. And here we have the feedstock in the fluidized or the gaseous state, and it's fluidized with the catalyst. We take it into this riser section here, which is basically a freeboard for separating the catalyst from the gas stream, but also for allowing for secondary reactions. So the catalyst is separated in these cyclones and falls down in the bottom. The gas is taken out and cooled. We take it into a fractionator. We end up with some heavies, which is called slurry oil. We end up with two heavy and light cycle oil fractions here. And the majority of the product goes into the into a separation unit to get rid of first the light gases, then the butanes, and we end up with gasoline. And then in a final column, we separate C3 from C4. And the catalyst, interestingly, is very, very quick in deactivation. So catalyst's lifetime for a single cycle is about 1 to 2 seconds. So the carbon or the catalyst that falls down here in the bottom of the reactor part is actually inactive and full of solid carbon. This catalyst is then taken into a regenerator where the catalyst or the carbon on the catalyst is controlledly combusted. So we use the catalyst with air. The carbon on the catalyst will be transformed into carbon dioxide. The catalyst will be heated up, and that is the heated catalyst that we allow to contact again a new set of feedstock. The catalyst fines are separated and the flue gas is let to atmosphere. The compressor and the expander here are just a single shaft unit to save electricity. And looking at operating conditions, we have about 500 degrees and 1 bar in the reactor part and 700 degrees and 2 bar in the regenerator. So higher pressure here than in the reactor. Catalysts was originally just solid acid, aluminum chloride, but in the mid-60s something happened, and that was with the introduction of zeolite material, where we can get shape selectivity, which remarkably improved the operation with higher activity and much better stability. And the shape selectivity is dependent on the zeolite's structure. So it's a macrocrystalline structure which allows for certain molecules to enter while other molecules are not allowed to enter. The only molecules that do crack is the ones that enter into the material. And looking at how this play out, we see that in the 50s with the aluminum chloride, we got some gasoline additional. We got also heavy carbon. We got lots of coke and light cycle oil. In the 1960s, we introduced high aluminum content, zeolites, and we got more gasoline yield, but also more LPG yields. In the 70s, there was an introduction of rare earth type Y zeolites, which gave further improvement in the gasoline yield. And now we're using ultra-stable type Y zeolites, which give about twice the amount of gasoline as the initial catalyst, but also some more gas, but also less solid carbon. So catalytic cracking is a unit operation to lower the fuel output from the refinery. It produces gasoline, but also lighter fractions like LPG and heavier fraction like light and heavy cyclic oil. These can be used as fuel oil, but also for making specialty chemicals like carbon black. Cracking of the paraffins, olefins, naphthalene, and the side chains in aromatics is what happens, and it's an endothermic reaction, and it's then supported by the exothermic regeneration. So the solid carbon that we form is combusted in the regenerator, and that heat is what drives the reaction. And zeolite is the catalyst. Catalytic reforming is a unit operation that takes a light fraction. So it's something that is already in the right boiling point range for being gasoline, but it changes the octane number. So it's an octane boosting operation. Remember, octane was the knocking or self-ignition propency for gasoline. So here we take something that contains straight hydrocarbons, and we turn it into branched, cyclic, or aromatic hydrocarbons. And in the process, we also get hydrogen. So it's something that supplies the refinery with hydrogen. And we get that through isomerization reactions. We get cyclization, so forming naphthenes, but also aromatization. And this is where we get the amount of hydrogen that we can use. We also get hydrocracking reactions. And if you look at aromatics, for instance, it's about 30 to 40% of the feed, but after production, it's 45 to 60%. And isomerized products can be, or straight chain products can be lowered from 45 to 55 to 30 to 50%. The catalytic reforming is endothermic, so it's an equilibrium gas phase reaction. We have problems with solid carbon formation, and it's solved by recycling some of the hydrogen. Hydrogen helps keeping the carbon formation at a reasonable level. We also want to avoid forming things that are less or lower than C5. So what we want to do is transform C6 to C11 molecules into branched, cyclic, or aromatic hydrocarbons. And for that, we've developed a catalyst with a dual functionality. So we have a alumina in the bottom. We have acidic groups to do the cracking reactions, and we have platinum to do the dehydrogenation reaction. And schematically, we take heavy naphtha with this research octane number containing paraffins, naphthene, and aromatics as per so. We put it through this reaction, 500 degrees, 5 to 25 bar with a platinum catalyst, and it consumes heat. And we end up with something that has a research octane number of about 90 to 100 with this amount of paraffins, some naphthenes, and a lot of aromatics. Then we have to be careful because there might be other restrictions to the number of aromatics, and especially benzene from a health and safety perspective, but that's another story. But looking at how this is done, we can do this in 3 different commercial processes. It's either semi-regenerative, fully regenerative, or continuously regenerative. And they basically work in similar ways, but doing the regeneration of the catalyst quite different, where you have, for the semi-regenerative, rather long catalyst life, but you need much higher hydrogen to hydrocarbon ratio, so much higher hydrogen in the inlet. You also do it at higher pressure. Fully regenerative, you have days to weeks, as is the same for continuous with respect to catalyst life. And you operate at milder pressure conditions and much lower hydrogen to hydrocarbon ratios, which lowers the flow through the reactor and the reactor volumes. Looking at the fully regenerative process, we actually start with having a catalyst in a lift pot. So we take the catalyst, we lift it, and we move it into a reactor. We take naphtha, we preheat it, we do the endothermic reaction, so temperature drops over the reactor. We then take it, we heat it up, and we do this several times to further the equilibrium, and we end up with our reformate. So this is where we come out with the catalyst, with the product, and we now have a much higher octane number gasoline than before. The catalyst, on the other hand, slowly moves through the catalyst bed. It's taking out from reactor 1 and entered into reactor 2 and slowly goes through there, and then to reactor 3, slowly through, reactor 4, slowly through, and finally it goes to the regeneration section, where we use air to remove carbon, but we also need to restore the acidity of the catalyst, so we add chlorine gas to it. And if you missed it, we also need to add hydrogen to our product to keep carbon formation at a reasonable level. So moving the catalyst around, doing full regeneration after it's passed through the catalyst reactors once. Quite neat solution. So catalytic reforming aims at increasing the octane number of the naphtha. It reforms alkanes to branched alkanes. It closes alkanes and makes naphthenes. It also aromatizes them. And there is 3 commercial processes: semi, full, and continuous regeneration. We use platinum-based catalysts, and all of the commercial processes need some kind of catalyst regeneration. Alkylation is another slightly odd bird in the reaction regime in a refinery, because it normally uses a homogeneous phase catalyst. Here we take isobutane and we react it with alkanes. So we want to use as much of the propene, butene, and pentene as we can to form highly branched alkanes, because they have very high octane number. So we have 2 effects. First, we have the very nice octane number gasoline product, but we also increase the liquid product yield. And from a refinery perspective, anything you can turn into liquid gives us more money than the gases. So it's an exothermic process, and it's a low temperature, low pressure process, and it's catalyzed by, as I said, liquid acids normally, but there are also solid acid catalysts. We use an isobutane feed in excess to the olefin, about 8 to 12 times. So we have to recycle the isobutane, and that's to avoid reaction between the olefins. And if you take and compare the most common acids, the sulfuric acid is the most common one. We use that at low temperature. An alternative would be to use hydrofluoric acid, which is then you have to be very cautious with hydrofluoric acid from a health and safety perspective. So you need to know that. Residence time at low temperature, of course, needs to be higher than for the hydrofluoric acid. But if you work with solid acids like zeolites, you need higher temperatures. You also need to go up in residence time, so you have 10 times as large reactors. But on the flip side, you can much easier separate the catalyst from the reactants and products. And aside from that, there is not really that big of a difference, aside from that the sulfuric acid consumption is much higher than the hydrofluoric acid consumption. An alkylation is basically the reaction of an unsaturated molecule with a branched hydrocarbon, paraffin, and it turns into different isomers of the resulting C7 hydrocarbon in this case. And for the liquid catalyst process, we have multiple reaction stages. We have long contact time from 5 to 30 minutes, actually 20 to 30 is only for sulfuric acid. The acid and the hydrocarbon is sort of an emulsion, and that means that we need to separate this from each other at the end using a mixer settler. And afterwards, we actually need to neutralize the hydrocarbon phase to avoid transferring the acid to other parts of the refinery. This part is, of course, made in stainless steel, but the rest of the refinery is not. We then separate the hydrocarbons from each other by distillation, and problems can be, as I mentioned, the consumption of acid, the corrosion, but also having sulfur or fluorine will contribute to pollution unless you get a 100% degree of separation. Process flow diagram. We come in with isobutane in excess. We heat it up slightly. We have a reactor mixer settler type system where we have cascading reactors. So we start with doing reaction in one section, we add the acid here, we go in with the alkene in the bottom to control and make sure that we don't get polymerization of the alkene. We then take the residual product and we use it to, or we wash it to get a nice, clean, low acid number product. We also do water cleaning to get rid of the residual caustic. We take it into a first column where we separate the isobutane and we recycle it. We also go into debutanizer to get rid of any N-butane that has been formed. And in the bottom, we have our nice high octane number gasoline. The last section here in the reactor is also a settler where the acid and the hydrocarbon is separated from each other with the hydrocarbon on top and the water sinking to below. And we also extract more isobutane and alkane here to recycle it. And part of it is also going in here to separate any propane that might have been formed from the propylene, for instance. So in summary, alkylation is an acid catalyzed reaction. It can be done either with a liquid or a solid catalyst, and we have to have corrosion and pollution in mind when we do the liquid catalyst operation, but also the consumption of acid. And for the solid phase catalyst, the need for co-feeding hydrogen for catalyst regeneration is a significant drawback. Hydrotreating. This is divided into two parts. It's either removal of heteroatoms like sulfur, nitrogen, oxygen, and metals. But we also talk about hydrocracking, but that would be in a separate section. So hydrotreating is normally done to protect downstream processes, but it's also for environmental concern. We need to get sulfur levels down to handleable or allowed levels. These are all equilibrium reactions. They are exothermic, and we make quite small changes in molecules compared to the other cracking type reactions. And if you look at the development of sulfur levels in the EU, before 1996, when we had the first European regulations or standards, we were allowed, or from 96, we were allowed to use, or up to 96, we were allowed to use 3,000 ppm of sulfur in the diesel. In 1996, that was changed to 500 ppm. In the year 2000, 350, and 2005, it was changed to 50, and now we're at 10 ppm of sulfur. But to be honest, it's actually quite difficult to stop at 10 ppm. So much of the diesel is desulfurized to very low levels because you can't really stop at 10 ppm. And the type of reactions that we see is mercaptans reacting to form the corresponding hydrocarbon and H2S, so reacting with hydrogen. We see opening of thiophenes, we see reactions of benzothiophene. We also see reactions with nitrogen, so pyridines reacts with hydrogen to form ammonia, and phenol type molecules containing oxygen will react to form water. This is done in either gas or liquid phase. It all depends on which fraction we treat. So naphtha, for instance, which is a light boiling point range hydrocarbon, we treat in a fixed bed reactor at in the gas phase, but heavier oils that we can't transfer easily to the gas phase, we treat those in trickle flow reactors. In trickle flow reactors, it's a notorious factor or fact that you need to make sure that you get really good distribution of your hydrocarbon over your catalyst. Otherwise, you might risk getting hotspots, and maldistribution might cause other things as well. Looking at the conditions, we look at about 320 to 380 degrees for naphtha, pressure 15 to 40 bar, could actually be lower, but for normal processing reasons we end up there. We have hydrocarbon to feed being somewhere 0.1 to 0.3 normal meter cube per kilogram, but that depends also on the sulfur, nitrogen, oxygen level of the feedstock. Weight hourly space velocity about 2000 to 5000. For the gas oil, slightly higher temperatures, 330 to 400 degrees. Much higher pressures, 40 to 100 bar, but that's to keep everything in the liquid state. About the same hydrogen consumption, and slightly lower space velocities to handle more severe feedstock. Basically, what we need to do is take our feed, we mix it with hydrogen, we go in and we do preheating, then we heat it again with the furnace to get it to reaction conditions. We then do multiple stage desulfurization, or whatever D we do. So we go through a first reactor, the reaction is exothermic, we form our sulfur, hydrogen sulfide, but to lower temperature again, we insert hydrogen, cold hydrogen gas as a quench, and we lower again the sulfur content, again forming more heat, we add more cold hydrogen in the middle, and finally we end up here with a high sulfur or low sulfur containing fuel and a higher temperature. And in some instances, we also see an exit stream here, extracting the hydrogen sulfide rich gas, adding fresh hydrogen and having a noble metal for doing the final step in the desulfurization, noble metal catalyst. We then do separation, high pressure, where the water, where the hydrogen sulfide and hydrogen is removed and separated from the hydrocarbons. The hydrogen sulfide is allowed to contact with water to form some sour water, and carbon dioxide and other things will go there as well. Part of the hydrogen sulfide, most of it, will end up in chemical scrubbing, where it's absorbed in an amine, and the H2S is sent for upgrading into solid sulfur using a Claus process, and the hydrogen is recycled. The hydrocarbon is then stripped in a stripper column. We add some steam, we take the naphtha out, but we also get acid gases remaining here because they're entrenched in the hydrocarbon. And the catalyst here is normally an alumina with cobalt or nickel molybdenum, and it's sulfidated to be in the sulfur state for the reaction. So to summarize, you use hydrotreating to reduce the heteroatom content, like oxygen, nitrogen, and sulfur. We use hydrogen to reduce also metal content of process streams. In that case, the metals end up in the catalyst, and the catalyst needs to be rejuvenated at certain points. We use sulfidated catalysts, and it's important that you have a certain level of sulfur in the gas to maintain the sulfidated state of the catalyst. Otherwise, they will lose in activity. And of course, how we do the reaction depends strongly on the stream to be treated. Like low boiling point can be done in the gas phase, high boiling point in the liquid phase. Finally, hydrocracking is when we take a heavier fraction, like heavy gas oil or vacuum gas oil, and we turn it into lighter ends, like naphtha, kerosene, diesel. And it's driven again by this increasing demand of transport fuel, and that we don't want heavy fuels coming out of the refinery. Heavy fuels end up in marine applications and other low value applications. And it's not that important if you look at light, nice crude oils. Then if you just do hydro skimming, you get more of the fuel oil, 44%, but with a complex refinery, you actually don't get that much more kerosene, gas oil, and gasoline. But if you look at really heavy crude oils, you can end up with a large amount of crude oil, fuel oil, which is a low value product, and ending up with much less of this and much more gasoline for this complex refinery type. And this is, as I said, important and more important when we turn into worse and worse crude oils compared to the nice sweet crude oils that we started working with in the industry when it was new. So hydrocracking involves cracking of heavy compounds with hydrogen present. It's a complementary process to the FCC. It's exothermic. There are equilibrium reactions involved. And the feedstock actually needs to be pre-treated with hydronitrification to avoid the catalyst for being decomposed. We don't see complete conversion, and the unconverted part is actually an excellent feed for the FCC. So what we do is, first of all, get rid of the heteroatoms, and then we turn aromatics into naphthalene. We crack on break rings, so hydrodecyclization, and we do alkane hydrocracking again, like this, splitting them with hydrogen present. And the catalyst, again, is one of those two functional parts with one acidic function, silica alumina, for instance, and one hydrotreating function, either nickel molybdenum or noble metal. Deactivation can be by metal deposition, and it looks something like this. So you have silica alumina, it can be a zeolite or some other type of support, and you have the active phase on top. In the hydrocracking, the feedstock is heated to about 330 to 430. We do this at 70 to 150 bar, and that's to keep, again, the feedstock in the liquid state. We do it either in a single or multi-stage configuration, and they can be either fixed bed, ebulliting bed, or slurry bed reactors. And yeah, you can see the operating conditions here, and also the catalysts down here. What we do is take the feedstock first, and then we go into the hydrotreating, again getting rid of the sulfur, nitrogen, oxygen part in multiple stages. We then take this and go to a flash unit where we get the hydrogen out. The ammonia is sent to acid gas removal. We go to a distillation column where we separate the gas from the naphtha from the middle distillates. And the heavy part of the fractionator is then what we take to our hydrocracking reactor. We increase the temperature, mix it with hydrogen, and then we do multiple stage reaction with intermediate quench to get rid of or lower the temperature. And then we cool it down and we go into the flash again. So hydrocracking, in summary, is decomposition of heavy feedstocks with hydrogen. It involves metal removal and nitrogen removal. It decomposes the heavy compounds to lighter ends, and we do this in one or several reactor configurations, and we use high hydrogen pressure. Future trends, we see a strong demand for increasing value of heavy fractions, but also the environmental aspects. Particulates, SOx, NOx are coming much higher in requirements. Energy efficiency is another one of those that is very much in the topic right now. We look also at the aromatic part in reformulated gasoline, so maximum 35% in Sweden, for instance, 1% benzene. We need to keep track of that. And of course, getting rid of the sulfur is important. But another thing that we need to be aware of is the handling of renewables and low blending of renewables. So what happens with ethanol and biodiesel in our mixtures? How do that change our acid number of the mixtures? Do we need to switch storage tank material, things like that? And we need to adapt the industry to handle these heavier crudes, complementing refineries with cracking, hydrocracking, but also coking. And hydrogen, when we increase our demand for environmental performance, hydrogen consumption becomes more and more important. The internal hydrogen production is too small, especially when you combine this with a need for doing hydrotreating of renewable feedstocks like triglycerides, tall oil, fatty acids, things like that. You need hydrogen production. That hydrogen production has to be integrated in the refinery. We need to make sure that we utilize the hydrogen in different exit positions in a wise way. Maybe it can be upgraded again or used in a cascading way, in a different way. And therefore, doing hydrogen pinches is quite common nowadays. So to conclude, refineries are very complex process industries. We see that there is a wide range of products coming out, and their distribution is to some part based on the current economic situation. So if there's a shortage of jet fuel on the market, you can steer your production to jet fuel. The crude distillation unit is really the heart of the refinery. The thermal processes are very important on the heavy side of the refining, and catalytic processes are really important for improving yield and product quality. With that, I'd like to thank you very much for your attention. Please send me any questions you may have via email. There will also be a follow-up email which provides you the slides as well as the recording for this webinar, and you can also download the slides from the client right now. With that, I would like to thank you again for listening and wish you a nice day. Cheers.